Thank you for your introduction. And I am Domenico Ammendolea, a PhD student from University of Calabria in Italy. So the work that I'm going to present is co-authored with Professor Fabrizio Greco and Paolo Lonetti and Dr. Arturo Pascuzzo. So common material used in engineering application suffer from internal cracks. Recent advances in computational field have permitted to write several numerical methods able to reproduce dynamic crack propagation phenomena. So this method can be classified in smart and discrete approach. The former represents the crack using a proper damage law, while the latter reproduces internal defects, including strain or displacement discontinuity, files into standard finite element formulation. Each method presents advantage and disadvantage, thus denoting that a unique and optimum approach does not exist. So now, currently, developing the advanced numerical approach able to ensure reliable prediction and achievable computational bounds are much required. So in this work, we present an efficient finite element modeling strategy that combines the moving mesh technique with the interaction integral method for reproduce dynamic crack propagation mechanism in quasi-brittle materials. The moving mesh technique, based on the arbitrary Lagrange LRN formulation, is suitable for handling random cracks easily, while the interaction integral method is used to extract fractal variable at the crack front. The HAL serves as an efficient method for tracing the geometry evolution of the computational domain caused by the advanced crack. Besides the spatial and material domain, HAL defines a referential system. A proper mapping function links the referential and the matter frame, which is needed to express the governing equation with respect to the referential or mesh configuration. The governing equation of the problems comprise two contributions. The first concern the solid mechanic problem, and the second is thus relative to the moving mesh problem, which include the Laplace regularization approach for reducing mesh element distortion. This problem is solved under two constraint conditions. One, avoid mesh motion on the external boundary of the computational domain, and the other impose the displacement of the crack tip. Finally, this equation derived from the fracture mechanism problem for identify crack onset condition and analyzing crack propagation phase. So MA integral expression can be obtained starting from the definition of the dynamic J integral applied to a closed contour surrounding the crack tip. For computational reason, the J integral is converted in equivalent domain integral. Here, Q is an arbitrary weight function which assumes a unit value at the tip and 0 on the other edge of the closed domain. The MA integral results from the J integral applied to the superimposed state formed by two admissible files, the actual one, for which dynamic stress intensity factor would evaluate, and the auxiliary one, whose solution is now. The MA integral represents the mood of them. Under this assumption, we derive this expression of the MA integral. We assume as auxiliary file the one of Williams crack tip asymptotic solution, where the velocity and acceleration files are 0. This involves a considerable simplification of the MA integral expression. Finally, the dynamic shifts of the actual state are evaluated using two interactional integrals, considering auxiliary states those of pool mode 1 and pool mode 2. An automatic algorithm manages this method. The analysis starts by defining geometry, material, and boundary condition. Internal cracks are represented by polyline. The hull moves the crack tip to simulate the propagation, and this movement must not change the shape of resistant crack. For this reason, the polyline is further fragmented near the crack tip by ending an extra node, thus forming a small segment that stretches during the propagation. After this, the code creates the mesh and starts the simulation, which involves a loading process. During each step, the dynamic shifts are extracted and used to assess crack initiation condition. When this condition are fulfilled, the dynamic propagation takes place. The tip velocity is evaluated through a classical fracture criterion. During the propagation, the elements around the crack tip distort because of the motion of the mesh nodes, and the remeshing process are required exclusively when mesh regularity is compromised. In addition, a tolerance to the angle variation of the stretchy segment with respect to the local crack system is imposed, and when this tolerance is fulfilled, the computational domain is updated. So the analysis continues until either crack arrest condition or the collapse events occur. Now, two crack problems are considered and developed to verify reliability and efficacy of the present method. The first example is a pre-crack rectangular plate under tension affected by dynamically advanced crack at constant velocity. This velocity has been assigned has a boundary condition without considering constraint detected by fracture criteria. We have used three different mesh configurations. Mesh M1 is refined around the tip and coarse elsewhere. The mesh M2 is entirely coarse, while the mesh M3 is refined everywhere. And the results in terms of normalized dynamics obtained utilizing M1 are compared with the analytical solution and the prediction provided by Chen et al. And the results denote that the proposed method is a good agreement with them. Furthermore, this graph compares the normalized six for the mesh configuration utilized. The results show that the proposed method ensures acceptable levels of accuracy in extract K1 regardless of the quality of the mesh. In addition, we have examined a combined case consist of an initial stationary crack that then starts moving at constant velocity. The analytical solution for both stationary and moving crack are shown in the lower left. Also in this case, the results are in good agreement with both analytical solution and prediction provided by Chen et al. Finally, in this graph is reported the percentage error between the numerical prediction and the analytical solution, calculated by this formula. These results highlights that the proposed approach evaluates K1 rather correctly during the mesh motion because the percent variation is less than 50%, confirming that effectiveness of the proposed strategy based on the MA integral in the context of the Ale formulation. So in conclusion, we present a novel finite modeling strategy for reproduce dynamic crack propagation phenomena in quasi-brittle materials. The proposed approach combines moving mesh methodology and the interaction integral. So the proposed model reduces the recourse to the remesh events, which typically involve substantial computational cost, and ensure accurate prediction. Finally, this work has showed that MA integral can work accurately in the framework of the Ale methodology. Thank you for your attention.